Hi, in this lectures, we are going to discuss a topic that we already study in statics, namely shear and moment diagrams. If you remember, when we talk about shear and moment diagram, we talk about a type of element subjected to bending, which is called beams. As a general definition, beams are slender elements that support loadings applied perpendicular to the longitudinal axis. Here is an example situation where beams can be used. You can see that a beam is used to support a brick wall. In this case, the weight of the wall will exert onto the beam in the direction perpendicular to the axis of the beam. In order to design the beam, we need to determine the maximum stress within the beam. For that, first we need to be able to determine the state of stress for any point within the beam. Let's size this point. Please note that when I say the state of stress for the point, I mean the stress on the side of the cube elements. Fortunately for the beams like this one, the state of stress for each point will not be that complicated. Instead, it will look like this. As you can see later, the normal stress, the green arrow, is the result of internal bending moment, and the shear stress, the purple arrows, are caused by the internal shear force at the cross section going through the point. The following is the visualization of the internal shear force and the bending moment at the cross section. Since we want to determine the stress for all the location within the beam, we need to find the internal shear force and bending moment for all such cross section. That said, the best way to visualize the result will be to use the so-called shear and moment diagrams, the topic of these lectures. Before diving into that, let us look at different types of beam so that we will understand the terminologies related to this type of member. As you can see, the beam on the left side are the basic type of beams that we learned in statics, where the support reaction can be found by simply using the equilibrium equations. On the other hand, the beam on the right side are more complicated, where the support reaction can only be found through an additional use of the compatibility condition, which we discussed in previous lectures. Now, here are the side conventions to be used when plotting shear and moment diagram. As you can see, if a beam is subjected to an external distributed load, the load will be considered positive if pointing upward and negative if pointing downward. As to the internal shear force, it is considered positive if it tends to rotate the beam clockwise after using the method of section. Finally, the internal bending moment is considered positive if it causes the beam to be concave upward. Now let us review the conventional method that we learned in statics to plot shear and moment diagram. To be specific, let us use the method for the beam shown on the screen. First, we will find the support reactions by plotting the free body diagram for the entire beam while replacing the distributed load by a concentrated load. Through the equilibrium equation, we can easily find the support reaction as depicted on the screen. One very important thing should be noted here is it is only acceptable to replace the distributed by concentrated load when determining the support reaction. The reason is they are only equivalent for that purpose. Once we find the support reactions, the correct free body diagram for the beam should be the following. Now, the idea to proceed with the conventional method is we will develop the shear and moment functions and then based on those to plot the diagrams. The variable of the function will be the longitudinal coordinate of the cross section. As you can see, since there are no particular changes in the geometry of the beam or the loading in this case, we do not need to divide the beam into multiple segments. In other words, the variable x on the screen will vary from 0 to 4 meters. Now, let us continue with the method of section. To write the equilibrium equation, let us replace the distributed load in the free body diagram by an equivalent concentrated force. Based on the equilibrium of forces in the vertical direction, to find the internal shear force V and the equilibrium of moment about the centroid of the cross section, to find the internal bending moment. Finally, we will plot the shear diagram and moment diagram based on those functions. You can see that the procedure is easy to understand and straightforward. However, you will see a potential problem when the beam is subjected to a complicated loading. Specifically, you will find that the conventional method in that case might be too labor intensive and time consuming. That is the reason why people came up with the following graphical method. To understand the method, let us first consider the scenario where a beam is subjected to an external distributed load of arbitrary shape as shown on the screen. Let us consider an arbitrary length element of the beam. Let us zoom in and plot the free body diagram for the element. From the equilibrium of forces in the vertical direction, we can see the relationship between the distributed load and the shear force written in the differential or integral form. From the differential form, you can see that the slope of the shear force diagram at the point is equal to the value of the distributed load at that point. In the same manner, from the equilibrium of moments about point O on the screen, we can see the relationship between the internal bending moment and the internal shear force written in differential and integral form. Again, from the differential form, we can see that the slope of the moment diagram at a point is equal to the internal shear force at that same point. As you can see later on, this relationship can help us plot the diagrams much faster than using the conventional method. Now let us consider the effect that a concentrated force or moment will have on the shear and moment diagram. To be specific, let us consider a beam with a concentrated force and a concentrated moment as shown on the screen. Let us consider a length element right at the location of the concentrated force and plot the free body diagram for the element. From the equilibrium of forces in the vertical direction, we can see a jump of the same value of concentrated force in the shear diagram. Specifically, if the concentrated force pointing upward, there will be a jump up when we go from the left to the right. On the other hand, if the concentrated force pointing downward, there will be a jump down. Now let us move the length element to the location of concentrated moment. Zoom in and draw the free body diagram for it. From the equilibrium of moments about point O, we can see a jump of the same value of concentrated moments in the moment diagram. Specifically, if the concentrated moment is in clockwise direction, there can be a jump up when we go from the left to the right of the moment diagram. On the other hand, if the concentrated moment is in counterclockwise direction, there will be a jump down. Now let us apply all this observation to the earlier example, with which we have used the conventional method. Let us see whether we will obtain the same diagram. Here is the beam we just mentioned. In the first step of the graphical method, we will also need to determine the support reaction. Now let us draw the shear diagram. If we go from the left to the right, the cross section at support A will be the first location of the diagram. Since we have a concentrated force at A, there will be a jump up from 0 to 2 kilonewton at point A in shear diagram. To continue, we will base on the slope of the shear diagram. The slope at each point is equal to the value of the distributed load at that point. If you remember the sign convention explained in a previous slide, for this example, the distributed load is constant, minus 1 kilonewton per meter along the axis of the beam. That says from point A, the shear diagram will go down with a slope of minus 1 kilonewton per meter to the other end, point B of the beam. And that completes the shear diagram for the beam. Now let us plot the moment diagram. Since there is no concentrated moment, there will be no jump in a moment diagram when we go from the left side of point A to the right side of point A. To continue, we know the moment diagram will have a slope of 2 kilonewton at point A, which is equal to the shear force at point A that we can see from the above shear diagram. Since the slope reduced from 2 kilonewton at point A to 0 at the middle of the beam, we can predict the shape of the moment diagram in that region. Based on the relationship between the bending moment and the shear force in the integral form, we can easily find the value of the bending moment at the middle of the beam, which is equal to 2 kilonewton meters. Now, if we continue from the middle cross-section of the beam, the moment diagram for the second half of the beam will be the following. As you can see, we complete the shear and moment diagram very quickly with not much calculation. Most importantly, the diagram that we obtain are the same as those obtained before with the conventional methods. To conclude these lectures, I hope you see the logics behind the graphical methods and will be able to use it comfortably. Thank you and see you in the next lectures.